Good afternoon, everyone. Today we are going to go over angular kinematics. Okay, so what is the difference in angular kinematics and linear kinematics, and linear motion and angular motion, right? So angular motion, all the parts move in the same angle, but they don't move in the same displacement. So what does that mean? So that means, like, if you look at this bicycle wheel over here, okay, linearly, when we looked at things, it was just this entire bicycle wheel moves this direction to the right. Okay, but now as we look at angular kinematics, we actually break down that bicycle wheel and we look at it from the point of all the spokes and the locations within the spokes. Okay, so if you look at the red circles here, you see that the inside red circle actually, as it would roll, would technically travel the same distance, but it would have less of a displacement. So it wouldn't have as much of a length because it's closer to the center. Okay, what we call that is the vertex there of the movement point of the chain. Okay, so that vertex or that axis of rotation is kind of our reference point. And then as we look at that inside circle, you see how close and small that line is, that radius to the center, while we look at the second larger further out red circle, and you see that that is a much larger radius. Okay, so when we look at angular kinematics, we're looking at, what motion is happening, but we don't really consider what is causing the motion. We don't look at that. We're just looking at the actual function, whereas in linear kinematics, we're looking more at what causes it as well. Okay, and then we look at the bicycle wheel, and it kind of shows us that example. Angular motion occurs typically around a fixed point or the axis of rotation or that fulcrum, like I was saying, and most movements involve translation and rotation. Okay, so you see how technically this translation would be a slide. So if you look at our cartwheel down here, you see that I am translating, I'm sliding across the floor as I do this cartwheel, but I also have a rotation happening with my legs. And then just like we do with the bicycle wheel, you can see that as I start here, my legs are going to travel from the bottom point down here all the way up, arc over, and come back to the ground, right? Whereas my hands go down and they stay relatively in the same place here, and then they're back up. Right, so if you look at just this part, these three middle pieces, and you see how much the leg moves versus how much the hands move. That's kind of the best example point right there. When you look at this and think of angular kinematics, how that kind of plays into effect. So then as we look at these angular kinematics, we look at angles, of course. Okay, so there's two planes that intersect at a vertex, or what we call the axis of rotation, typically in biomechanics. Okay, think the thigh and the lower leg, and then the knee. So if my thigh and my lower leg are my 2 points that are creating my angle there, like yo, the middle point would be my knee, which would be my axis or my vertex, or where all that motion is going to actually occur, that hinge, right? Be mindful in knowing that as we talk about angular kinematics within biomechanics, what's actually happening is we're dealing with imperfect anatomy, right? So if you remember from anatomy or kinesiology, a lot of times what you have is that tibial plateau in that knee it's not flat, it's not completely flat, it's not completely smooth, and then the femur, that's not exactly smooth and flat as well, right? So when we have that screw hole mechanism as well, when we go and extend our knee, right? So it kind of rotates and translates a little bit on us as well. So it's imperfect. So that as we're looking at range of motions, and as you're a strength coach or a regular coach or a physical therapist or an athletic trainer or whatever you choose to be, or an OT, and you go and you start working with patients, that's why sometimes just a slight rotation of a foot or a shoulder, internal, external rotation, might actually make that joint feel much better, or that joint motion feel much better or less painful, because you're changing that center. So what that means is, as that whole joint moves through its rotation and it's occurring, those translations are occurring, that actual focal point within that knee joint is actually going to shift left, right, anterior, posterior, as it moves through that motion. So just be mindful of that as you go into therapeutic exercises and exercise prescription and personal training and things like that, that will occur, and that's why those small little tweaks are effective, because of things like that. Okay, and then one of the big units of measurement within angular kinematics is a radian. And a radian is a measure of an angle at the center of a circle described by an arc equal to the length of the radius of the circle. So what the heck does that mean? So what that means is, if we have our beautiful circle here, okay, there it is, beautiful circle, okay, and we're looking at a radian. Okay, here's my fulcrum, or my vertex, or my axis of rotation. Okay, imagine that's a straight line. Okay, and we'll say here. Okay, that's not really, actually, you know what, I'm going to erase that, just so that this is more of an effective demonstration here. Okay, so we'll say here to there, and we'll say about there. Okay, so what a radian is it's really a ratio of the radius here of the circle and this arc. Okay, so what it's saying is that this radius is the same distance or same length, okay, as this arc. So if I was to take this arc and straighten it out, it would be the same as this radius, and that's what they call a radian. And so as we look at it here, theta equals S over R, and that equals 1 radian. So the arc length of R along the diameter and the radius, right? So exactly what I just said. So what that means is that is 1 radian is 57.3 degrees. So to convert an angle to a radian, you're going to divide it by 57.3. So I'm going to take, let's say, a 90-degree angle, right? And I want to see how many radians it would be. I would take that 90 degrees, I would divide it by 57.3, and I'd get 1 point something, right? It'd be, sorry, my math off the top of my head is not great. So, lost my calculator here, there it is. So, 90 divided by 57.3 equals 1.5 radians, right? So we have 1.5 radians as what that would equal. Okay. Now let's take it the other way, and I have radians, and I'm trying to turn that into degrees. So if I have 1.5 radians, right, I'm going to multiply that by 57.3, and that's going to give me 90 degrees, and that would give me my degrees. Okay, so just as we're going along, radians really don't have any value to them other than that reference right there. They're, as they say, like non-descriptive. Okay, it just gives you that value. Okay, it doesn't have a distance other than that 57.3 degrees. So biomechanics, right? So what are we looking at here? We're looking at 2 different types of angle. Okay, I'm not going to dive too much. The book actually dives in, the Hamill book dives in pretty well on how to actually calculate these absolute and relative angles, but I don't think that they're practical for us in this point of view, because of we're not going to do that. We live in the age of technology now that we are going to, more often than not, use some type of technology to really create these. But I want you to understand what they mean. Okay, so an absolute angle, what is that? That's the angle of a body segment and a fixed external point. So they typically, if you look over at figure 9.6 that I took from the Hamill book, you see that they have this fixed horizontal line, right? And they always assume that when you're doing these, you're looking at it from the right side, so the camera's looking at the right sagittal plane here. And if you go the other way, it's okay. It's just so you know, for their point of reference, that's what they're talking about. Okay, there's two methods of calculating this, and typically what they do is they place a coordinate system at the proximal end and measure from the horizontal, right? So the close end and measure from the horizontal, or they put it at the distal end and measure from the horizontal. Okay, so up here, and then they measure it from there. Okay, and then they produce a tangent to find the angle or the segment angle. So they have their coordinates, and then they draw here, right? And then they take their tangent with their arctan, and then boom, there it is. And that's how they get the angle. It's typically a addition and subtraction of the coordinates, of the two coordinates. So you take here and here, or here and here, and you kind of figure out what is happening. And then you have the relative angle. Okay, so relative angle is typically what we do a little bit more, because we use our goniometers, and that's kind of how goniometers work more off your relative angles than your absolute angles, because we're not necessarily doing it off a horizontal plane. We're not going to measure the hip range of motion like in figure 9-6 by holding it horizontally there, right? We're going to do it with the trunk and the thigh. So that's what it means by the relative angle, is using two segments of the body. Okay, so like in the shoulder, they're using the y-axis here and then the x-axis here. But it could be in any type of position. Technically, you could even have this, if I'm looking at the elbow, which is what they're doing in this top A picture, I could technically have my arm out here, or I could bring it in over here, and I'm still measuring that same angle right here, right? And that's what relative is. Now, there are many different coordinate and angle definition systems in making this, so consistency among different studies is a little bit difficult, because how I would do this is I would lay a coordinate graph over the top. Sorry, my squeaky chair. Coordinate graph over the top, and I would plot my points from that point of view. We don't really do that. So now we're going to look at how you actually calculate these joint angles, right? So these joint angles are calculated by looking at the theta of the desired joint, and that's typically then subtracted. You subtract the theta of joint A and theta of joint B for what you're trying to find. All right, so if I'm looking at the hip and I want to find theta of the hip, what I'm going to do is I'm going to take theta of thigh and subtract that from the theta of the trunk. And that's going to give me the absolute angles, and that's going to give me what I'm looking for here, right? So if you look at it here, it kind of shows you all these thetas on where you find these thetas over on the picture of the left with the man. Okay, and you can see how these angles are calculated. That's why we learned our joint angles before, so that we could really understand that. So the hips that way, the knee would be the thigh and the leg, so above and below the joint, and then the ankle would be also the leg and the foot, right? So I'm looking down here. Relative angle calculations should give the same, but it's measured a little bit different between the two segments versus a fixed object. Okay, so what does that mean? That means that if you look at the picture to the right, it's the same, right? See, I wrote it in 914. This is again from the Hamill book. That if you look at angles A, C, and E, they're all absolute angles. So angle A here, C here. You see how it's got the dotted line to show the horizontal or the fixed point that it's trying to reference. Okay. I know I said earlier that it's a horizontal because that's what it looks like in this picture, but really you're just using any fixed point, and that's what you use as your reference. And then as you calculate all these angles here, it should, because I use this whole coordinate system outside of it that really kind of says when it's in this coordinate, you're going to, it looks kind of like this. Okay, so how it looks is here, here. So when you're in this angle, you don't do anything. That's coordinate 1, coordinate 2, 3, and 4. Quadrant 1, 2, 3, 4. And then when you're over here, you're gonna like subtract 180. Over here, you're going to add it. Let me show you here for an effective example here. So when it's in quadrant 2, it's my theta angle that I get, and then I'm going to add 180 to that number, and that's going to give me what it is over here, because that would be a negative, and that would give me a negative theta 2. If this is confusing, don't stress about it, because I'm gonna show you some other stuff here. If it's over down here in theta 3 or quadrant 3, it's gonna be theta theta 3 plus 180, and then if it's over here quadrant 4, theta 4, right, it's going to be plus 360 degrees is what you get, because you'll see that these thetas are a little different, and that's kind of how you get it. Over in theta 1 or quadrant 1 here, it's just going to be whatever you get is what you get, and that's how you got to kind of work off these plots. I understand it's a little confusing, but I'm going to make it real easy for you in a few seconds here. Okay. So relative angle calculations should give you the same, but it's measured between two segments versus a fixed object. So we look here, right? And now we have, you look at angle B, right? Angle D down here, and angle F down here. Okay, and you notice that these angles are a little bit more familiar to us, right? Because this is what we do with our goniometry. So angle B, angle D, where I would measure of the knee, right, knee flexion or extension, I would kind of measure the thigh and the lower leg. As I look at the ankle, I'm typically, as you guys remember, we're doing the lower leg and then the foot, right, and we're checking how much that angle is. Okay, so we don't do too much absolute angle in healthcare or in coaching and things like that. We look more at relative angles because they're going to give us the same as those absolute angles. Okay, so why I said we don't need to worry too much about the math, because we live in a technology age, right? I like this app called Angulus. Now I have this terrible screen mirroring, and my wife was nice enough to let me take her picture, and I'm using the free one, so you have to look at it this way. Sorry, and it's going to be a little crooked. It is what it is. Right, but on the app it looks a lot clearer. It's pretty solid. Okay, and you can pick 3 or 4 points. You can change the width of your lines here, and you can import pictures, or you can import even videos, right? So I could take your videos that you guys have given, and we can take it and drop that into here. So the ones I'll be posting of you guys for your final analysis, you can do it this way too. Okay, so if I wanted to look at, let's say, the hip, right, I can move this point right to about her greater troch right there. I can take the top part, and in the app you can actually rotate this picture so it's not so awkward. Run it right through her shoulder and her ear, right, because we're doing that posture, right, and it goes through the ear, through the acromion, down to the hip. And then if I wanted to do like an absolute angle, I could technically do that right here, right, and make it with the horizontal. And don't worry about getting the line perfectly straight. You can tell it's pretty straight on the phone because this line is solid. When it's moved, you can see it kind of jaggeds up on you a little bit. You can kind of see, maybe you can see that, like there, you can see how that line's jagged now. And you just kind of get there. If it's off a few degrees, if you watch A and B, if I'm down here versus here, it's just a few degrees. It's not going to kill anything that we're doing, but it gives you that idea, right? Or I can do it my relative angle, which is what we mostly use, right, and use it through her knee, and I get my angle of about 79 degrees is what she's at in hip flexion during this squat motion. It's kind of fun, and you can change it, and you can move it down to here to this ankle. And this is what I'm saying, where yeah, the math's good, but a lot of time in our day and age, and if you're really diving into biomechanics, you're going to use these tools because they're just more effective, they're faster, they're more efficient for us, and it really helps us. Okay, and you're looking, you see your A and your B, so your B angle, the external angle back there is different. And as you zoom in, you can get a little more effective. Now you see here, this is part of my error. And it says she's at 96.1 degrees, but it definitely doesn't look at like she's at 96.1 degrees of this squat, right? And that's just because I'm at a bad position on her as I took this photo, right? So my angle, I'm looking at it kind of coming from above down. I'm looking down on it, which is going to change my angle there. So you really want to make sure your camera angle's a little bit better than mine was during this user error here. But either way, it still works for our purposes, right? It gives us an idea of what's happening, and you want to try and get as accurate as possible. I'm not going to hold you accountable and say, oh, you're off a few degrees, this is a problem. You know, just as long as you justify everything and you acknowledge there's limitations in what we have and what we do, that's fine, because we're going to be functional evaluators of our posture and our biomechanics in any thing that we get into, unless you are a biomechanist and you're working in a lab and you have sensors that you can put on people. This is what matters right here. This is the most important part. So now we're going to get into angular motion vectors. Okay, so how they call they call that a polarity of a vector is what we're calling when we talk, or what we describe it as when we talk about angular motion. Okay, so what is the polarity of a vector? It's typically what they call the right-hand rule. So you look at which way it's spinning. Okay, so they say right-hand rule, it's going to look like my left on here, right? They say, right, so you kind of spin your thumb is what they kind of talk about right here, right? So when it's thumb up, it's counterclockwise, and we call that positive. Sorry, this way, right here, right here, right? Counterclockwise, thumb up, positive, right? That's good, positive, right? And then if we go down and we spin it clockwise like that, that would be a negative polarity. So clockwise, down, negative. Thumb up, counterclockwise, and that's what they call, that's hard for me to do. Counterclockwise, they call that negative polarity. Okay? And then we look at the position and the displacement. And what is that? So in 2D position, typically you're looking at the picture. This is kind of like we did just a second ago with the still frame of my wife doing the squat, right? It's a 2D position. We don't have any z-axis, right? So with no anterior, posterior, we have front and back, up and down, right? So x and y axes. And that's, you know, the x-axis would typically be like a lateral medial rotate or movement, and then we have the y-axis, which is your up and down, right? So just think of your graph there, x, y, medial, lateral, and then y is your vertical. Okay, and then in a 3D position, we add the z-axis, which adds the anterior, posterior reference. So now it's forward, back, left, right, up, down z, or up, down y, left, right, x, forward, back, z. Now you'll notice that these planes correlate with our sagittal, coronal, and transverse planes. Like if you look at the shoulder, for example, right? If I have rotation of my shoulder here, that happens here in the y plane, that's happening. Or if I put it down, now I'm rotating in the z plane, or I mean the z plane, x and z plane. I'm sorry, x and z plane, AB and AD duction in the YZ plane right here. Can't really see it, but up and down, right? AD, AB duction, Y and Z plane, and then flexion and extension is in the X and the Y plane. Alrighty, now we're going to move on to angular distance versus angular displacement. Okay, so what are those? Okay, angular distance is the total distance traveled of an object around its vertex, and then that is calculated by adding up all the arcs. Then we have angular displacement, which is the sum of the total arcs. Okay, but this number is different than angular distance. I'm going to draw a picture that's really going to clarify this. But displacement really is more about it's not going to ever go over 360. Okay, so let me jump to the slide and show you guys real quick. It's going to be easier if I just draw it out and show you. Okay, so here we are. I'm going to change colors because I'm tired of that one. So let's go red. Okay, so if I have a pendulum, right, let's say here's our point here, and it comes here, pull it back and it starts here, right, and it moves through, here's straight down, here's over here, okay, we'll say it's moving like this, right, we'll say this total arc here is 70 degrees, which would make one of these small ones 35. Okay, so you got to go back to displacement and distance, right? What's the difference, right? So our total distance is here to here. So we're looking at the object, the ball at the end of the pendulum on distance, right? Because total, it's moving all the way over here 70 degrees. Then it moves back, we'll say, to, let's say it eventually stops. Let's just say it goes one time over and stops in the center again. Okay, so it moves over here and then comes to rest right here. The total distance it traveled, if you look at this line, was that right there. So we would take this angular distance and say it went 70 degrees because it came all the way out here, and then it came back to center, which is 35 degrees. Okay, so then we would add those up and we would get 105 degrees. Okay, and that would be our angular distance. Okay, but if we look at displacement, right, we're looking at just the line that it traveled. Boom, the max distance. Okay, if it only went to here, that max would only be 70 degrees of our angular displacement, right? Because we're not measuring distance, we're just seeing how far it displaced total. Does that make sense? That'll never be more than 360 degrees, right? Because if I have a pendulum here, right, and I have this object right here, it's never going to be more than 360, because if it's rotating around and this was a perfect circle, which it's clearly not, right, it's just going to keep going. So it would only be displaced 360 degrees because it just keeps going. Whereas if we're looking at our angular distance, it can have multiple, and that's where, like, if you think of a skateboarder or snowboarder, right, and they're doing 360s and 720s, right, that's more distance is what they're measuring there, because it goes around multiple times, and we add all those 360s up on top of each other. And that's what it means when we're talking about angular distance versus angular displacement. Okay. Okay, so the last part that we are going to go over is, sorry here, just getting my slideshow back up. Here we go, boom, boom, there you go. So the last part we're going to go over is angular speed and angular velocity along with angular acceleration. Now these are fairly similar to that of linear speed, linear velocity, and linear acceleration. The only difference is now we are dealing with angles in different Greek letters, to be honest, for the most part. Okay, so angular speed. Angular speed is the angular distance traveled per unit of time. Okay, so it's typically in degrees per second often, but then because we're talking about angular kinematics, we also want to change that into a radian. Don't forget at the end, okay? Angular velocity, that is Greek letter omega, or the little w, and describes the rate of time change in angular velocity. Okay, so that is omega equals the change in theta over the change in time, okay? And you would convert that to radians. And then lastly, angular acceleration is the rate of angular velocity change in the reference to the time. Okay, so that is the Greek letter alpha, and that is alpha equals the change in angular velocity over the change in time. So let's go ahead and show you what that does here. Let me pull the whiteboard up. Okay, so we have for angular velocity, right? We have W, that is my great omega there, equals change in theta over change in time, right? So if I have W and it equals, we'll say, let's say I went from 62 degrees and then I ended up at 34 degrees at this angular velocity here, right? And then I take that and I'm going to put that over the starting point, which is we'll say 1.3 seconds is when I began. Okay? There you go. And then I would subtract that from my ending time, which was, I don't know why I did that. We'll say it was counting down and it was 1.25 seconds. We'll say it was like a shot clock. Okay? Once again, I am a Picasso, I know. Thus, omega would equal 28 degrees over 0.05 seconds. And then as I divide that, omega would equal 560 degrees per second. Okay, and then how I would change that into radians would be W equals 560 divided by 57.3, and that would give me my radians. I'm not sure off the top of my head what that is. Let's look. 560 divided by 57.3, and that would be 9.7 radians. So I would be going omega equals 9.77 radians per second. Okay, so that would be my final answer there. Okay. And as we move to the quiz, this is kind of what I want to see here. Your math, so I know if you got it right or wrong as well. Okay, because I'm pretty much just going to give you guys a couple problems and we'll take it from there on what is right and what is wrong. Okay, and then the angular acceleration, the rate of angular velocity change, and the change in time. So pretty much I would take alpha, and it's almost the exact same thing, right? So a change in angular velocity. So if I'm moving from, we'll just say 62 degrees per second to 34 degrees per second, right? Then it's going at the same time change, right? It would equal the same unit of acceleration. Does that make sense, kind of? So if I just change these values for all our purposes here, you would just do the same thing. Set change in time, in velocity, change in time, subtract, that would give us that, and that would be your acceleration. Okay, does that make sense? I hope so, and if not, we will discuss more in class. I didn't want to hit you with too much. I thought I'd just kind of introduce these concepts here, and then we're going to dive further into it in class on Tuesday. Okay, alright everyone, I'm going to post this up along with the previous PowerPoint, and we should have those in Blackboard this afternoon, and then the quiz will be up, and just have that in by the end of the day. Alrighty, hope everybody has a great weekend, and I'll talk to you guys later.